एंड एडिशनली एहन चीज सब जे कि अपन कम्युनिटी के बेसी छाप नहीं छे स्पेस साइंसेस में, ओई में पंकज जी लीड कर रहल छथि आई के वेबिनार। उनका बहुत बहुत स्वागत एंटा के एग्जीक्यूटिव कमिटी के तरफ से, एंटा फैमिली के तरफ से। आई अखन जे फेसबुक में दुनिया के लोग देख रहल छथि ओ अहाँ के लाभान्वित हेता आई के प्रोग्राम से। ई कहत पंकज जी अपने के पुनः बहुत हार्दिक अभिनंदन जे अपने गछलौं एंटा के प्रोग्राम के लेल। वी आर रियली इंडेटेड टू your kind acceptance to present today's webinar. Thank you.
Thank you, Prajita ji, and thank you, Anta. May I share the screen, if you guys don't mind? Yes, I don't have the permission here. Okay, I do. Wonderful. Okay, so I'll run this presentation in English. I guess our primary audience is based in the United States. But then if you have any questions, please feel free. I can answer your questions in English, Nepali, Hindi, Maithili, any of these languages. Kato to mix bhai speech. So, but primarily I have presentation English mein run kara ja rahal chhi. Kato ki samasya hoy to please let me know. Okay, can you guys see my screen? Okay, my screen dekh rahal chhi sab? हमर स्क्रीन देखा रहल यहाँ सबके एटा इंट्रोडक्टरी स्लाइड हेते जे पर करू भर छै someone.
Yes. Okay, did you see the screen?
Yeah. Yes, we can actually.
Okay, wonderful, thank you. Like she just introduced me, I'm a physics researcher and mentor. I mostly work on satellite launch systems and near Earth objects. In short, I'm an aspiring physicist. If we have time, we can talk more about my background later, but for now, let's focus on the topic. So the topic today is early perspectives on aerospace and astronomy. Well, what does that really mean? I would say let's look at my agenda, and that should make it clear. So my plan is to start with something basic and then gradually build on it. So I will introduce I'll introduce space itself. I will try to discuss how we define space, where does it begin, and then we'll move into some of the academic and career streams of the space sector. The next topic I would like to talk about is a sample space exploration mission. So for the sake of example, I'm taking Mars 2020 mission. We'll see how these academic and career streams that we have discussed converge into planning and executing a mission of this nature. So every mission from Apollo to rovers to Cassini to Saturn, every mission has some planning, some execution. It involves a lot of career and academic streams. We'll talk about these later, but for now, let's see what the next subtopic is. Okay, then we'll change the course, and I will focus on two big areas of space sector. So there's aerospace, which is more of engineering, and there's astronomy, which is more of science. So I'll explain both of these fields with some fundamental concepts and some examples and some tools. And then if you're a student who's trying to pursue astronomy or anything in space, I'll have some helpful tips and links for you. I'll discuss those. And after some discussion, I'll conclude the presentation and open the floor for questions. Okay, are we on the same page? Everyone good? If you see me looking at two different screens, because I'm working on two different screens, I'm sorry, I might not just focus on the camera. So before we go into this actual agenda, let's break the ice with a fun little story. Start here. When I was young and I wanted to be a scientist, I looked around and I saw everything was already invented. So satellites were there, airplanes were there, medical stuff were there, everything was already there. Now, what's there for me to do, right? Everything is already done. This is one question that I struggled with growing up as a science enthusiast. And I'm sure a lot of you kids probably struggle with this question too. A lot of things are already done. I found the answer to that question years later, but I'll give you a little clue, and that should be helpful. Let me open this little animation here. Okay, can you guys see my screen now? I'm in a different window. should be a picture of an astronaut in black space, in black background. Can you see it? Okay,
Yes,
wonderful.
you can see your screen.
That's very helpful. Thank you.
Yes.
Okay. So that's the average size of a human being, adult human being, right? An astronaut is adult human being. That's the average size. I'm basically trying to compare the relative sizes of stuff in universe. And next thing in line we have is a Hubble Space Telescope. It's about the size of a big SUV or I would say a small school bus. And then comes the Space Shuttle, which is slightly bigger than a school bus. And then the International Space Station, which is about the size of a football field, slightly bigger, but that's comparable. So compared to a human being here, the size of other artificial stuff is slightly bigger. Now let's move into more natural things. That's asteroid. Okay, now we have moved into dwarf planets. So compared to a human being or anything human beings have created, you see a dwarf planet is much, much bigger. Now let's look at some of these other stuff. The moon, small planet. Okay, that's our planet Earth. So compared to anything that humans have created, the Earth is much, much massive. It's much, much bigger, right? But then we have bigger planets. We have Saturn and Jupiter, and then we have the sun, which is really massive, right? So compared to the sun, the planets are really, really small. So the sun should be big, right? In fact, no. We have other stars that are much, much bigger, and they're much, much heavier than the sun itself. The next star that you see in line, the white star here, I guess it's Sirius. Yeah, Sirius A. Yes. So this is the brightest star in night sky. It's slightly bigger than the sun itself. But then we have more bigger stars here. We have Sagittarius. Let me go to a different one. Okay, then there's this massive star called Betelgeuse. I guess this is about 100 times bigger than Earth, and this star is supposed to explode in a few hundred years, and it will create a huge. Yes, Nancy, I guess you had a question. I can't hear you.
I've heard, like, I did some research about Betelgeuse, and like I know it's gonna explode, and like it will create like it will be like it will be so big, it will be visible to Earth, and it will be like so pretty.
Yes, and it will. The size of it, I would say, would be slightly smaller than the moon. You would see, you wouldn't just see a point of light. You might see a cloudy, hazy, but that's hundreds of years from now. Even if the star, let's say, explodes now, the light will take a lot of time to reach. But let's move on, and then I'll come back to the questions. If you want to save your questions till then, that would be very helpful. I want to encourage questions though, but let's save those for the end. Okay, and then we have other bigger stars, and then that's a black hole. And of course, there are bigger black holes than that. And then we have nebulas, and then larger nebulas. And then finally, we have galaxies. And then there are clusters of galaxies, right? So we started from something really small. We started with man-made objects, and then we moved to these massive big stars and galaxies. And so started with a human being, man-made objects, then these bigger, massive stuff, and we went all the way to galaxies. But are the galaxies big enough? Actually, no. There are clusters of galaxies, and there are billions of galaxies in the universe. And the whole observable universe has, I don't even know how many billions of clusters there are. Okay, so that's the whole observable universe. Now let's get back to the question that I said I had growing up, that everything was already invented and discovered, and there was nothing left for me. Let's get back to that slide. Okay, so everything that you just saw, all the massive stars and galaxies and clusters and everything is just 1% of observable universe. So this yellow strip right here, this little yellow strip, this is everything that you can see and feel and touch. Everything that you just saw, all these massive stuff, billions and billions of stars and galaxies, it's contained in that 1%, less than 1%. 74% of dark energy, sorry, 74% of universe is dark energy. Is it really dark? No. Anytime anything is unknown in astronomy, we call it dark. So the dark side of moon is not, it's not actually dark, it's just invisible from Earth. And then 22% of the universe is dark matter. About 4.5% is matter that we can understand. So ordinary matter made of electrons, protons, neutrons, things like that. But out of that, only 0.5% of the total mass is what's visible to us. So everything that you saw is less than 1%. That represents something incredible. Remember the question that I had, everything is already discovered? Well, 95% of the universe is unknown. This 95% of things remains to be discovered, to be invented, and one thing leads to other. For example, once we found out electrons existed and they could flow and electricity existed, see how it changed the world? I mean, everything runs on electricity now. From 95% of these unknown matter and energy, there will be some more inventions, more discoveries, and the civilization will just change. I don't know if we are even capable of discovering everything, but it's changing rapidly. One of you could discover what's in there and then probably win a Nobel Prize, right? Okay, one of you is winning a Nobel Prize. Discover this and you have a Nobel Prize, I promise you that. Okay, let's move to the next slide here. Okay, so now that we know we have this 1% that's observable, why would we even bother about just discovering or exploring that 1%? Why is it so important? There's some philosophical, some existential things that matter, and then there are some practical applications. Is the reason why we explore space. To explore is human, right? I mean, it's in our very nature. We discovered continents, we populated them, we cross-populated them, repopulated them. We used to wander around Earth, and then it's in our very nature to spread out, right? So it's the same thing with the universe. Planet Earth is the cradle of humanity. The human race can grow up here for a few centuries, just like a baby grows in a cradle for a few months or few years, and then eventually it has to step out of that cradle and explore the world, right? It's the same thing with humanity. We can grow up on planet Earth for a few years, let's say a few centuries, and then eventually we will step out. We'll become an interplanetary species someday. Then there's also this thing called planetary defense. Right? What if the Earth is about to be hit by a comet or an asteroid? How do we prepare for that? So the better knowledge we have about astronomy, aerospace, all of these things, the better prepared we are. So dinosaurs, they didn't have education system. They were just a species hanging on Earth, and they were not prepared for a strike by asteroid, right? If it's the same for us human beings, what's good? Right? We are much more intelligent. We have much more tools. We have science. We have engineering. If we are not prepared, if we are just as prepared as the dinosaurs, how helpful is that? Right. So we also explore space for planetary defense purposes, and these things are mostly abstract and long term. But there's a lot of practical applications that you can see on day-to-day basis. Things like satellites, GPS, microprocessors. A lot of things that go into your smartphone where either directly invented in course of space research or as a byproduct of space research itself. Then there's medical stuff, things like CAT scans. Then we have smoke detectors. A lot of these things were invented in the course of space research. There's a story I would like to share with you. Back in the 50s and 60s, the United States and the Soviet Union, they were locked in a massive space race. The Russians were really powerful. They sent the first man into space. They sent the first satellite. They sent the first woman. They were powerful. On the other hand, the United States they were just starting their space program. It wasn't that comprehensive at all. But Americans were able to land people on moon, and the Russians were not. And there's an interesting reason why they were not able to do this. The Russians had bigger, massive rockets, and they could launch bigger stuff in space, and the Americans did not. They had smaller rockets, much smaller rockets, and they had to miniaturize everything. So in course of miniaturizing all these processors and computers, putting them on board, they invented microprocessors, a lot of semiconductors and electronics. In order to land somebody on the moon, especially not just probes, but human beings on moon, you need to be able to crunch your data in real time. So you cannot send your data back to Earth and expect them to crunch the data and send it back to the moon and land human beings like that. You should have something that's small enough that fits into a rocket or a probe and it lands on the moon itself. So the Americans were able to miniaturize stuff, invent microprocessors, and land people on the moon, and the Russians were not, even though they were really powerful, right? So it changes, it shapes human civilization in strange ways. You know what they say is this space sector might not make the price of bread cheaper today, but it will change the course of civilization tomorrow. So a lot of things that happens in the space sector it's not visible right away, but you see the long-term effects. Okay, now that we have agreement that we should explore space, let's see where to begin. Where does the space actually begin? For a lot of practical purposes, space begins at 100 kilometers. There's this imaginary line at 100 kilometers above Earth. We named it after, I believe, German physicist von Karman. Yes, so the reason beyond 100 kilometers of altitude is called space. Now, this is a generally accepted definition. It's not a formal definition of the space. A lot of agencies have their own workable definition. For example, NASA and the US Air Force, they use 80 kilometers as their boundary for a lot of purposes. So if you're an Air Force pilot who flies a SR-17 class aircraft, you basically wear a spacesuit. You get astronaut wings. You fly a fighter jet, but you are an astronaut beyond 80 kilometers. That's for NASA. A lot of other agencies, they use 100 kilometers. Now, this region has some properties, some essence of space. The actual space doesn't begin here. A lot of gravity is gone, a lot of atmosphere is gone, and there's a lot of actual work in the aerospace sector happens much beyond that. For example, the International Space Station is located at about 370 kilometers in average. Sometimes the gravity drags it down and their orbit has to be boosted up. But a lot of communication satellites, they have to cover the larger curvature of the Earth, so they are much, much further. They're about 20,000 to 40,000 kilometers in distance from Earth. That's where a lot of these magic happens in aerospace. What about the moon and the planets and other objects, right? What about the natural objects? Well, the moon is about 400,000 kilometers away from Earth. I guess it's 384,000 kilometers. And the planets are even much, much further. This also helps us make an important distinction here. So the study of natural objects, now I would like you to focus here. The study of natural objects like moon and the planets, their surface, their atmospheres, is astronomy. The study, the design, the manufacturing of artificial objects like probes, rockets, satellites, rovers, that's aerospace. That's more of engineering side of things. So design, manufacture, maintenance of spacecraft, aircraft, or rovers, anything that's more of aerospace, more of engineering, more of hands-on stuff. Astronomy, on the other hand, is more of science, more of theory, more of observational stuff. Aeronautics is a huge part of aerospace, the design, manufacturing of aircrafts. But in today's presentation, we'll try to focus on space only. But like I said, aeronautics is a huge part of aerospace industry. Now, what are some of the career avenues that can lead you to a career in aerospace? Well, since it's aerospace engineering itself is big, right? That's the first one. And then there's electrical engineering, and then there's mechanical engineering, building stuff. You need a lot of mechanics. You need to build a lot of components, and mechanical engineering is important. Then you have to program them, right? So software engineering is important. Robotics, mechatronics, that's important. So any of these career fields here can help you work in this sector. In fact, the biggest pool of talent in aerospace is in electrical engineering. So electrical engineers and technicians, they form the biggest talent pool in aerospace sector. And then there's astronomy. A lot of things in astronomy is observational, computational. So if you're looking at a star or a nebula, you gather a lot of data, and then you have to crunch that data and then find results from it. That's computational astronomy. So you have observational astronomy, computational astronomy. There's theories that you develop, so that's astrophysics. You want to study the possibility of life in universe, the possibility or origin or evolution, anything related to life. That's astrobiology. It's a big field these days. And then career-wise, you could, if you study astronomy, you can work for space agencies, you could teach at universities, you can do your own research. There's a lot of things you could do. But job-wise, there's a lot of job prospects in the aerospace sector than there's in astronomy, I'll be honest with you. It's a little sad, but yeah, that's how it is. There are more jobs on the aerospace side than on theoretical astronomy side. Let's go to the next slide here. Okay, now I would like to discuss a sample mission, a sample space mission to see how these sectors that we just talked about, electrical engineering, mechanical engineering, or pure astronomy, how do they converge to plan and execute space missions? Space missions like Apollo 11, right? The mission that landed people on Moon, and then we have these rovers and satellites. How do these sectors converge together and make this happen? So for the sake of example, I'm taking Mars 2020 here. This mission was launched last year in the middle of pandemic. It was launched, I guess, on July 30th, and it's landing in about 2 weeks. In fact, it's landing on the 18th of this month, so about 10, 11 days from now, after 7 months of cruising. It has a range of about 20 kilometers, so it will roam around Mars and collect samples and stuff. It can move up to 20 kilometers. That's its life. But usually it goes much beyond that. We have seen that with past rovers. It goes beyond its natural life. Okay, every mission has some science goals, right? And this Mars 2020 mission has well, it does a lot of stuff, but its goals can be categorized into four main objectives. The first one is geology. I'll explain all these individually in a little bit, and then astrobiology, sampling, and then prepare for future human space missions. So to prepare for people to land there. Now let's talk about these individually, and that should make it clear. The first mission goal of the Mars 2020 mission is to explore its geology, Mars's surface, the rocks, the dust, and everything. And you just don't want to focus on one side. You just don't want to focus on, let's say, a lake bed or rocks or just the dusty part. So that's why the range is so big. You want to explore the Martian geology and see how it has evolved over time. Understanding the geology of Mars could be helpful for us in understanding the geology of Earth itself. So that's why it's important to study geology. Now, who would you need to study geology? You would obviously need people who have background in geology, right? Geologists, physicists, engineers, people of that nature. And okay, the next goal is astrobiology. We basically try to find signs of life. There has been a change in approach. The earlier missions to Mars, they focused on, we had suspicion that life exists on Mars now, right? But that has gradually changed. The evidence that we have now, it suggests that life probably did exist, but it's not there anymore. So the change in approach is that we used to look for present life. Now we're trying to look for past life. That's the second objective of this Mars mission. So who would you need for a mission like this? Of course, biologists, microbiologists to be more specific, right? People who can identify signs of life in the past or now, planetologists, a lot of people. So we need a geologist here. We need biologists here. Next goal is sampling. So this is the first, I would say this is the first major mission whose objective is to actually collect samples from a planet and bring it back. Now, this cannot happen in just one phase. So this particular mission, it will drill holes and collect sample from different areas and gather it at a place. And future missions, so this rover will drill holes and gather the sample at some place, and future missions will collect the samples, bring it to space. There will be a spacecraft that's waiting, and it will capture that sample and bring it back to Earth. In fact, China just did this with the moon about 2 months ago. They collected samples from the moon, and there was a spacecraft that gathered the sample and brought it back to Earth for research. Now, once you have sample, you don't want to spend everything right away. Technology changes really fast, right? So you don't want to spend everything with the technology that you have now, right? You want to save some of it, and in the future, when you have better techniques, better experiments, better equipment, you want to spend some of those later. That's sampling. And then, of course, we want to prepare for future missions. The most feasible method that we have in mind is we'll build domes with artificial environment. Earth-like environments will have domes. There will be oxygen in there. So pretty much a closed dome with environment that's very similar to Earth. That's the next mission. And you would obviously need engineers again to build this. There's some key observations here. And I want you to pay attention here. There's some key observations, right? So one of the observations is the space sector is actually really, really diverse. You have engineers, data scientists, physicists, geologists, biologists, all of these people working together to make it happen, right? And then it doesn't matter what your background is. Some of the common denominators that a lot of people use is mathematics. If you want to work in the space sector, maths would be good. But I'll come back to that later. A lot of ideas get communicated in terms of programming. So programming is used, right? And then the third and most important observation here is a lot of people that work in the space sector are not astronauts. Did you see any astronauts working on this mission? No. I mean, there might be in some advisory roles and other stuff, but astronauts are not directly involved in a lot of space missions. A lot of people that work in the space sector actually work on the ground. They work in control rooms, labs, and other stuff. In fact, only 555 or 56 people have been to the space, and that's out of hundreds and thousands of people that work in the space sector. So, I mean, there's a common myth that if you work in this sector, you'll be astronaut. No, that's not true. A lot of people actually do not become astronauts. But if you really want to be an astronaut, what do we do? I will give you three pathways. I will give you the journey of three different astronauts and see how their paths were different and how they were common. The first example that I took was astronaut Joseph Kerbin. He finished his bachelor's at 21. He was a doctor at 25. 26, he becomes a military flight surgeon. At 33, he joins NASA. And then eventually at 41, he becomes an astronaut. So he started with philosophy and then eventually became astronaut at 41. Mark Kelly, he started at 22. I guess he was in the Navy at that point. I'm not sure, but he eventually joined the Navy and then the Marines. And at 28, he had a master's in aeronautical engineering. 32, he joins NASA. 37, he becomes an astronaut. Right, and then we have somebody from our side of the world, Kalpana Chavla, right, famous astronaut who tragically died in the Columbia incident. She finished her bachelor's at 20. She was really sharp, and she was probably one of the most academically accomplished astronauts, I would say. So at 20, she had a bachelor's in aeronautics. 22, she has a master's in aerospace. 26, she has a PhD in aerospace from University of Colorado, and 27, she joins NASA, right? And at 34, she becomes an astronaut. So you see their career pathways were really, really different, all these three astronauts. But there's something common between them. They're all experts in their field. So if you really want to be an astronaut, you should have a two-step goal. The first step is to become an expert in your field, right? All these three people are experts in their field and astronauts later. So whatever you like doing, designing, building, studying science, theory, anything, try to become an expert in it. That's the first step of becoming an astronaut. There's no direct way to, apply for astronaut corps and then become one. I mean, even sometimes the application opens. I think the last time that there was an application opened was in 2015 or 2016. They pretty much asked for people who had science and aeronautics and aerospace background. But they expect you to be expert in these fields already. You cannot just become an astronaut without having something in the background. So try to become expert. That's the bottom line. Okay, now, so if you're a student who is trying to go into one of these fields, right? Astronomy or aerospace or engineering or science, anything, the first thing you should really, really focus on is dive deep into their curriculum. The space sector is not small. It's really diverse, and there's a lot of things that go on. So if you're trying to join a school, a university, try to focus on their catalog, research as much as possible. I'll give you some examples. Let me close this. Okay, so this is the course catalog of PhD astronomy at the University of Washington. This is my school here. So if you see the list of their courses, there's astronomy 101, there's exploring the moon, the interstellar matter, and a lot of things in pure astronomy and theoretical side of things. This whole course catalog. I'll send you all these links, so don't worry. You'll have all the resources that you need. So its catalog, course catalog is mostly just theoretical stuff, observational stuff, mostly astronomy, right? Now, you might want to work in the space sector, but you might not be interested in this. It's totally possible that you would like space, but you would not like astronomy. You might like more of engineering side of things. This is the course catalog from MIT. This is more of engineering. So aerospace engineering, it has a lot of design stuff, a lot of computational stuff, signals, fluid dynamics, things of that nature. So do your research. If you want to join the space sector, find out where your interest is. You might not be interested in theory, you might not be interested in engineering, one or the other. So dig deep into their curriculum. And then there are some degrees that are just generalized courses, and it doesn't focus on anything specific. I would say try not to join courses like this. Try not to join degrees like this. It will give you a degree, but it won't give you specific set of skills to succeed in space sector. And I'll send you, like I said, I'll send you all these links. Okay, more helpful tips. Okay, we already talked about diving deep into their course catalogs and curriculum. The next important thing is to communicate. If you're joining a school, communicate with the current students, former students, their science clubs, anything. Communicate with them, get involved. There's a lot of research, especially if you're based in the United States, there's a lot of places you can get involved with. There are science clubs, there are institutions. A lot of people are actually very helpful if you're willing to learn. So get involved. One of the reasons I think I was able to reach this far was I was always involved. I did not have too much resources, but I was always involved with science clubs or science fairs. I was always doing something. So getting involved is really important. And like I said earlier, you should focus on math, science, programming, and communication skills. At some point when you study, at some point your math and programming become your language. So if you open any higher level book in physics or engineering or anything, you would see a lot of mathematical expressions. You will see a lot of equations. You will see less of literature. So math becomes your language at some point. Programming becomes your way to communicate ideas. So if you're a young person trying to go in this sector, focus on math, science, programming, and communication skills is important. If you want to succeed in any field, it's just not aerospace. Communication skills, it could be written skills, it could be spoken skills, but communication skills is important. Stay focused, stay persistent, I would say. Now, there's something I would like to tell you. What if your math is bad right now? Your math teacher just hates you and you're failing your math classes. What about that? Should you just quit aerospace? You should just not even explore it? That's not true. It's way too early to judge now. You guys are way too young. Everything that you study in high school regarding math can be covered in a few months. So as long as you are focused, you are ready to work hard, you will succeed. Even if your math is bad right now, don't worry, you will get there. But I should also caution you something. Our whole education system is designed to filter out talent than filter in. You'll realize this much later. So don't try to fall too behind in math, I would say. Even if it's bad and you're trying hard now, just try not to fall too behind. That's the more important thing here. Another myth I would like to bust is there's a myth that the participation of girls, female, there's low participation compared to boys. That's not true. It's changing fast. It used to be true, but there's a lot of girls, there's a lot of female participation in aerospace and engineering and these sectors. In fact, I will tell you a personal story. All my first line supervisors from now till now, from my first job to the military to data science and a lot of sectors that I've worked in, all my first line supervisors have been females so far. So don't fall for the myth that girls have not succeeded or they're not in this field. It's changing fast. I mean, at this point, it doesn't look very good, but it's changing very fast. So girls, thumbs up. Okay, what's next? Okay, 3 things that you will hear a lot from adults in your family. What do you want to become? Where do you want to go? What do you want to do? The most important question here is what do you want to do? What do you spend your time, most of your time on day-to-day basis, most important. Where you will eventually go, what university, what place, what you will become is for later. So if you want to be a doctor, your focus should be on caring for people. learning stuff, and then you become a doctor eventually. If you want to be an engineer, your focus should be on designing stuff, right? Building stuff, learning tools and software, things like that. And then eventually you'll become an engineer, astronaut, or anything. But the most important question is what do you do on day-to-day basis? And that will define everything else. Now, it all might not always work with your plan. You might plan just your PhD, you'll be done with your PhD at 26, like Kalpana Chavla, and then you eventually become astronaut, but the reality might be different. I mean, the picture here is just a depiction. I mean, you might not have a boat, you might have a helicopter or anything. This might not be a mountain, it might be a big boulder that's a hurdle for you, but it's the usual case here is that life is not smooth. You know, you'll have some successes, some failures, but as long as you are ready to stand back up, you will succeed. Okay, now I'm changing the course of this presentation. Now I'll focus on the two sectors that I discussed about, aerospace and astronomy. So on the aerospace side, I will discuss some concepts and some tools that would be helpful for you. And then I'll do the same on the astronomy side. Now, in the time that we have, this cannot be a comprehensive class on any one of these topics. So I will introduce you to this topic. I will let you know where to go, but then you have to explore on your own. That would be a whole different. If I focus on just one tool, it would not be very helpful for you. So I'll introduce you to these topics. It might feel like drinking through a fire hose. You might see a lot of material thrown at you for now, but you know, I promise you, if you go and explore on your own, you'll find these easy and simple. It's not that hard. Okay, so the most recognizable entity in aerospace is a rocket. Everyone knows a rocket. I mean, there are probes and other things, but the most recognizable machinery entity in aerospace is a rocket. Rocket. There are different types of rockets. There are different sizes and shapes and everything. But there's something common between all these rockets. If you see here, they all have a nose cone, they all have a body tube, and they all have fins. Right? There's some things that's common. Some things don't change. The shapes, the sizes are different, but the same. If you really pay attention, it's almost the same. The design might look different, but the shapes, like I said, it's pointy little tubes with a motor and then payload and everything. These rockets are more professional, more sophisticated. Let's look at something simpler. Let me introduce you to a sounding rocket. A sounding rocket is a smaller rocket that mostly goes to near space with an experiment or a payload, and then does some measurements. Sounding basically means measuring in physics. And like I said, we have most of these rockets have a nose cone. They have a bay for payload area. It's mostly the nose itself or the shoulder of the nose, and then you have a body tube that carries most of the other parts, the avionics, parachutes, if they're involved, and other parts are here in the body tube. And then at the end, there's a motor, and then you have the fins that's there for stability. Now, if you really want to build a rocket, right? If you want to assemble a rocket, what are the things you should be looking at? There are structural components, like I said, the nose, body tube, fins, motors, things like that. And there's some functional things, right? How would this fly? What do the electronics look like? How do you gather data? How much stable this would be? And the good news is that you don't have to do all that by hand. There are a lot of software. There's a lot of tools that's available for you to design these things. I'll introduce you to one of these tools, but it doesn't have to be that, right? As a NASA representative, I'm not supposed to endorse any commercial product. I'm just using this software called OpenRocket, for example, but there are many other tools. There are paid tools, there are free tools. I would let you explore those. There's some tools that are really professional and sophisticated, but you have to pay for them. But the tool I will be demonstrating today is called OpenRocket, and it's free. Let me actually go to OpenRocket. One moment. Okay, so this is the website that will get you to OpenRocket. It's really simple. So if you click on download, if you go to this link, I'll send you these links, by the way. So if you go to this link and click download, it takes a few minutes to download and install on your computer. And sometimes it might not feel it's a safe link, but I've tested it many times. My students have tested it. It's totally safe. So go to openrocket.info. I'll send you this link, don't worry. And then download it. And what you'll end up is a design suite that looks like this. At first, this looks a little complicated, but trust me, it's simple. Once you get to know this, it's a simple interface. This basically has just 3 menus here. The rocket design part that gives you the parts that you can add to it. And then there's motors and configuration that will let you add a motor to it. And then flight simulation part will tell you how fast your rocket will go, how much it will accelerate, how far it can go, how stable it will be, things of that nature. So just these 3 things here, right? Once you download Open Rocket from here, and then open it, this is what you should see. And then after that, it's really simple. You go to rocket design, and then you always start with a nose cone. The reason we start with a nose cone is that everything else is referenced from here. So any distance that you would measure is referenced from the tip of the nose for a rocket. And then you add other parts. I added a nose cone. So I basically went to rocket design and these parts appeared. I clicked on the nose cone and a nose cone appears. Then add a body tube. We'll configure those later. And then add some fins. Then anything that you want to add to this rocket, you could just click on these parts and it will come to the body tube. Now you can, the parts that you have added, they can be individually, they can be configured. So if you want to configure the nose cone, let us say, you double click on the nose cone and it gives you this window that lets you change its parameters. So how long you want it to be, I don't want the nose cone to be that long, so make it short or make it long. If I want to, I can change the shape. Can make it conical, ogive. I could make it more parabolic. Yeah, so you could basically change the properties of your nose cone, the part that you're configuring from here. It will also let you pick the material you want, the finishing and everything. And it's the same for all the other parts. So the body tube, let's double click on that. Let's change its length here. See, simple as that. It's just like a little video game. It's even, I would say it's simpler than a video game. You just have to explore on your own. And the diameter you could change. And the same thing for any other part that you add, right? I mean, I cannot design this whole rocket now, but it takes about 30 minutes to an hour just to design a rocket of this nature. So I'll let you explore on this one. I'll send you the link and then you can explore. There's also some tutorials that's available online. I will send you those too. But once you are done with the designing part, you should end up with something like this. This one I built earlier just for demonstration. So it has a nose cone, it has a body tube where you can add more parts from here, and then it has a motor at the end, the fins, and yes, and then you have a sounding rocket. This is actually a functional rocket. It works. You can actually build this and then fly it. Every single thing here is defined. Like the material that's used for the nose cone, how is it fin? What does the weight look like? What does the finishing look like? You know, how does that affect the stability of the rocket? Everything can be configured. Click on a part, configure it. Double click on it, it will let you change its properties and everything. Let me look at a 3D view of this. Yes, I haven't added much parts to this. It's a lot of hit and trial. So don't worry if you mess up something. What's the worst that could happen, right? Just close it and open it again. That's the good part with working with software instead of hardware. If you have hardware, we're actually assembling these parts. You screw up something, then you have to start over. But with software, you could make a lot of mistakes, learn from them, and then do it over. So that's what it looks like in 3D. I mean, you would have more parts here. Whatever you add here will look different than what's appearing here. And then with that rocket, it tells you how much stable that rocket is, what's the maximum speed here on the bottom, what the acceleration is, a bunch of other things. I'll let you explore this by yourself, because if we do it now, it will be boring and it will take away a lot of our time. So let me close this Open Rocket thing here. Now you don't have to use Open Rocket. There's a bunch of other software that's available, and it's on the slide, and I'll also send you the links. Let me close that, and let me get back to the presentation. Okay, so we had a rocket that looked almost like this. You had these parts here, and then you're able to change the parts. But a few things that you have to be mindful right away when you start is like I started with the nose cone. could have a lot of shapes. You could have a pointy shape that's really, really conical. You could have something that's flat. You could have something that's more parabolic, something that's more ogive. The conical shape will give you the biggest speed, right? You want rockets to be fast, and the conical shape will make it fast. But the speed is always not in your favor. Your rocket might not be able to sustain the speed that you're targeting for. Your best interest is in having a shape that's a little more rounded. In fact, the most common shape in industry is ogive, a shape that looks like this. It's conical, but at the same time, it's a little rounded. This is there are two good things with this. The first thing, it avoids the rocket from going too fast, and then it distributes the heat. So when you're going that fast, you pretty much suffer a lot of friction, and there's a lot of heat here on the top. And ogive shape will help you, a rounded shape will help you distribute that heat evenly. A conical shape will not be able to do that, and there's a possibility you might catch fire. That's the nose. Same thing with the fins. If you want your rocket to be more aerodynamic, you could just use flat rectangular wings. If you want it to be fast, you could use more as of swept towards the back fins. And there's other options here. I'll let you explore this. And everything that you see here is in OpenRocket. Once you open it, you can click on these parts and configure them. Okay, now that you have a rocket that's ready to fly and it's in flight, the most important thing for a rocket when it's in flight is how stable it is. There's a lot of things that goes into stabilizing a rocket, but the key for it is to have the center of gravity higher than the center of pressure. I'll explain what that is. I believe a lot of you will understand what center of gravity is, right? It's the point where the weight of anything balances. So if you have a stick, if it balances at a point, that's your center of gravity, right? Center of pressure is where aerodynamic forces, forces like lift and drag, the pressure of the wind, the aerodynamic things that are working on the rocket, the place where those forces balance is called the center of pressure. Just like we have center of gravity, we have center of pressure. The key to stabilize a rocket is to have the center of gravity a little higher than the center of pressure. And these things you will get in OpenRocket. It will indicate where your center of gravity is, and it will tell you where your center of pressure is. So the key to stabilizing a rocket is to have the center of gravity higher than the center of pressure. But how high, right? The optimal width here is the diameter of the rocket itself. So if the gap between these 2 points is about, one moment, let me get a laser pointer. Okay, so if the gap between these 2 points is about the diameter of the rocket, you have optimal stability. If it's too wide, then your rocket is too stable, but it doesn't go too far. If it's too narrow, then it's unstable. So the optimal gap here would be the diameter of the rocket itself. And that's theoretical stuff. How do you test it practically? Well, you can create a mock-up of your rocket. You can use plywood or cardboard, anything, something that's very similar in weight and size with your rocket, right? And then swing it with a string. Attach a string in the middle and then swing it. If your rocket is stable in that swing, you're fine. Your rocket will be stable in flight. But if it wobbles or flips, anything like that happens, then there's a problem. And then you can make adjustments. You can add some weight or change the shape of the fins, and then gradually see how you become stable. Again, the instruments that you have, it can be packed differently. So the wider the rocket is, the more expensive it is. So if your electronics is packed something like this in a cube, you will need a rocket that's really, really wide, right? Instead, you could pack the same electronics, same instruments in a narrower fashion like this in a CANSAT. So it depends on what you're targeting for, what your payload is and how you're designing stuff. But the same exact electronics, same exact instruments can be packed differently, and then your rocket design can be different. Okay, that was aerospace. We discussed some concepts, and then let's look into astronomy. In fact, I will start astronomy with the tool itself. This tool that I will be demonstrating today is called NASA's EYES. And this is fun, especially for young kids like you. It's really, really interesting. It won't take you to space, but we'll bring the space to you. Okay, this tool is called NASA's Eyes in Universe. In fact, let me send you these links real. Give me a moment. So I'm posting some links in the chat window. And I'll give you a few minutes to copy it. A few moments, I would say. Minutes would be not very helpful. Let me find my chat. One moment. My chat window is lost somewhere. It's here, I know. Give me a second. Okay, I didn't want to forget this, so I've just posted the links in chat window, and you can copy this later. You'll have time. There's 4 or 5 links. Everything that we discussed is here. There's Open Rocket that we saw earlier, and then there's this NASA's Eyes on Universe. Okay, so for NASA's Eyes on Universe, you pretty much you can just Google this, and then it will take you to that page. If you click on it, and you already have the link, so you don't have to actually Google it. It's already there. Click on that, and then you will end up here. And then you can download this. It takes a few minutes to install. It's simple and it's safe. And then this window will open here. And it takes a few seconds to load, and if there's any updates. Okay, I just want somebody in the audience to confirm if you can see this.
Yes, I can see this. We can.
Okay, wonderful. So this tool is called NASA's Eyes on Universe. I'm focusing on the solar system for now. So it basically lets you explore the whole solar system from your desktop. And this is real time. This is graphics, but it's real time. And your friend here on this whole window is the home button. Anytime you feel lost, you click on home and you'll get back to this. And it lets you see the big picture of the solar system. And you can click on any object and explore it. For example, Saturn is here, so let's double click on Saturn and see. Let me zoom out. Let's look around Saturn. Okay, that's Saturn. That's a lot of its moons that's going around, and then you can also see other planets and other objects in the background. But then again, I'm on Saturn. How do I go back? Home button, right? This is your friend. I like the planet Mars, so let's click on Mars and see. This, in fact, is the satellite that's about to land. So this is the probe this is the rover that's about to land on Mars, I think on the 18th. So about 10, 11 days from now. Okay, the menu here on the bottom, it gives you a lot of options to explore. So the first one is information I. If you click on an object and then click I, it gives you information about that object. And these other things will help you navigate in real time and speed it up and things like that. We go back home. So I hope you guys remember how we got here. So we opened that link, NASA's Eyes, and then we downloaded the little plugin, and then we had this window that opened. And like I said, the home button is your friend. You click on home, you get here, and then you explore the object that you want to. For example, if I want to go to Jupiter, I double click on Jupiter. And I can see the planet. I can speed it up, or I can see it in real time. You can do a bunch of other things. But if you want to get more comfortable, if you want to see that the tours that's already there, you go to Tours and Features. And this will give you a whole bunch of tours that's already there done for you, and you can explore. Now I'm speeding through all these tools, but trust me, once you explore this on your own, you will find it simple. So let's see one of these missions here from the tours and features that's on the top right corner. It takes a little time to load sometimes. It's coming up. Okay, this is the Voyager mission. It has passed the solar system. I would say the planets, not the entire solar system, and it's into deep space. And the menu here lets you explore more from this. So these are the pictures on the top right corner here. These are the pictures that the mission took on its way. So this is when it was launched. This is when it was passing Jupiter. I think this was a long time ago in the 1970s. Then more pictures. This is when it was passing Saturn. And more, right? It was when it was passing Neptune and then eventually went. So the pictures that's taken from the mission is here. Then you can exit back to the solar system and explore on your own. So, okay, I'll send you the link, but you have to explore all these on your own. This is just a little demo. But is that the entire solar system, the 8 planets that we see? Actually, no. Hold on. So everything that we know about planets is here. It's in that the ring of 8 planets here. This is what we recognize generally as the solar system, but it actually does not end there. The Kuiper belt, which is at the boundary of solar system, is much further than that. And there's this spherical cloud of objects, little objects, ice, pieces of ice, dust particles, a lot of comets. They form this huge cloud around the solar system. So what we recognize as solar system is this little part here in the center. But the actual solar system is spherical. There's this thing called Oort cloud that has a lot of icy small objects, but might be small planets as well. Actually, this is the source of a lot of comets. So a lot of things that you see in universe as flat is actually not flat. There's usually a cloud of dust or interstellar gas around it. So most objects in the universe are actually spherical, even if they don't look like. So that's our solar system. That's how big the sun was, and then we had stars that were much massive than the sun, the thing that we saw earlier. And then you have galaxies that has billions and billions of stars like this. And then you have clusters of galaxies, and everything that we see is here in that 1%. Just to take you back to that first slide. We have a slightly more time, so I'll introduce you to one more tool, and then I will try to conclude this presentation. There's this tool called, hold on, it's here somewhere. Okay, so a huge part of astronomy is observation, right? I've been looking through telescopes, taking pictures, and then analyzing those pictures. There's this tool called Micro Observatory from, it's a collaboration between Harvard University and NASA. They have remote telescopes that you can use to take pictures. Again, this link is there. And this does not require any download. You just pretty much go to that link. It should be in the chat window, and you click here, and it gives you all this menu here. And then you can observe entity that you want to. For example, Jupiter is not available tonight. What's available tonight? Let me see. Oh, you can observe Mars tonight. So let's click on Mars. And hit observe. Okay, and then it gives you how long do you want the camera to expose. So this is an actual telescope camera that will take the picture for you. It's, I think this particular camera is based in Arizona, in the desert where you have clearer skies. And let's see how long you want to expose it. Okay, 0.05 seconds seems optimal. 1 second, it might be too exposed. So let's stay with 0.05 seconds. No filter is fine, or if you want to add filter, it depends on what you are observing. And then continue. Okay, it will ask for your email address. You enter your email address and then submit it, and it will send you the pictures in a few days. So anything that you want to observe remotely is available here. And then if you're a little more sophisticated, if you want to analyze those images, process it further, there's more tutorials and trainings and everything here. But I've sent you the link, explore this on your own. Like I said at the beginning of this presentation, it's literally not possible for me to run a comprehensive class on these tools. So I'm introducing you to a bunch of these tools. I'm giving you some hints, but you can explore them on your own. If they were complicated, if they're not doable, I would not share it with you. But these things are totally simple. You can take your time and explore on your own. Okay, we are running out of time, so I will try to conclude the presentation here. We'll end this presentation with one of my own projects, actually. This was my undergraduate capstone project. Let me go here. Sorry, I'm working on multiple screens, so it might look weird. Okay, this was a probe that I sent with a weather balloon to near space and collected some data from, and I added a camera to it just for fun. It's more of show off than actual science experiment. So I added I hung on a camera and some experiments to a weather balloon and flew to near space. This was about 8-9 years ago. So this was my previous university, sorry, it's going up. The actual video was about 2 hours, but I've made a short clip out of it, about 2 minutes, I guess, 2 hours, yeah. So it's going to near space, goes up to 100,000 feet. Approaching burst altitude. Okay, that was the indication for the recovery teams I had on ground. We had teams that tracked and recovered this probe. So that was indication for them. And this thing blasts at 109,000 feet. Like I said, the actual video was about 2 hours, but this is just shortened into clips. And out of all that empty space, it finds a little puddle of water and lands in there. So out of all that empty space, like hundreds of kilometers, it lands in that water. But that was expected. We knew we had a lot of lakes back in Oklahoma, where I went to my undergrad, and then we knew it could land in the lake. So that was planned. Everything was waterproof, and it was designed that way. Okay, so I think we are towards the end of the presentation now. Okay, so let me quickly recap what we did. I tried to introduce you to some the different streams in the space sector. I talked about some of the engineering tools and concepts, and some of the science tools and concepts. And you're supposed to explore on this on your own, so don't count on me on that. I seriously didn't have enough time to make this a comprehensive class. We talked about the Mars 2020 mission. We saw how these sectors, they converge and plan and execute these missions. We looked at rocket design, and then we looked at NASA's eyes on universe. Then we also looked at astronomical scale, how things are relatively small or big. And then I gave you some helpful tips, like focus on math, stay persistent. If your math is bad now, don't worry, work hard, you'll get there. Communicate, things like that. And then I guess that was all the presentation, all the content that I have. Yeah, it went a little more than an hour. But yes, that's everything I had for you guys. Now I'll open the floor for questions. For you, I'll start with a stupid question here. Look at the slide. So if you go camping and you look at the stars, you look at the sky and suddenly you see a lot of stars, it basically means somebody stole your tent. It's not that serious. That was a silly question just to break the ice, but now more intelligent questions from you guys.
Nancy.
Here,
like you showed us like how you made like a tool you made that goes up in space. Like, how did you make it? Like, what materials did you use?
the video that you saw then.
Yeah.
So I had the first part to that is a weather balloon. The weather balloon can fly really high. It goes anywhere between 70,000 to 120,000 feet. And it's usually used to predict weather. They send probes and they measure humidity, environmental parameters, things like that. So I used a weather balloon, and then I hung a lot of instruments to it. So I designed a small box, a box that was waterproof for the reasons that you saw, a waterproof box of foam, and then I had instruments inside there, and then I flew it with helium. So the balloon was filled with helium. You can fill it up with hydrogen, but it's a little dangerous. Hydrogen can explode, and helium is lighter than air, so it lifts up, and it takes about an hour to, less than an hour to go to the max altitude, and it explodes and it finally falls. I attached a camera to it to take the video. The camera was for the purpose of the actual experiment. That actual experiment was in the box. But you can find tutorials to making things like these online. Like I said, you just have to get involved. Everything is there. Yeah, feel free to unmute yourself and ask questions. I'm here.
Dr. Pankaj, we have got a question in Facebook chat. That is asking, black hole comes under which energy, dark energy or dark matter?
See, black holes, first let me explain what dark is. Dark is unknown, right? Things that are unknown, we just define them as dark. A few things about black holes we understand. We understand there's a lot of gravity around it. So that's known, that's not dark. But there could be other dark energies around a black hole that we don't understand. And we could categorize them as dark energy. Same thing with the matter. We know some of the matter that's collapsed in the black hole, but there could be things that's not known, and we can call them dark. So it's really a combination. Things that we understand, it's fine. Things that we don't understand, we just categorize them as dark. It's basically unknown. A black hole is a combination.
So Dheerajji, Pankaj just said that he's yet to become a doctor.
Oh yes, I just wanted to make sure. I don't have a PhD yet. I start PhD this year.
Okay, Pankaj, there is one question from Prabhatji. It's on the chat. How can engineering students how can engineering students learn into aeroscience internships? Are there any portals available?
Yes. So I would say the place where I live at in Seattle, we have Boeing here. So you go to the website, you pretty much pick any aerospace company, go to their website, and they always have opportunities available. Especially if you're planning to do something that's unpaid, it's not that hard. Paid positions, salaried positions are hard to get into in aerospace companies. They look at a lot of factors. But if you're just trying to get into internships to begin with, it's available. Go to their websites, go to an individual company's website that are willing to work for, and then find an internship. And there's a good chance that if you're good during the internship, they might hire you.
Dheerajji, I have asked the kids to raise their hand and ask by themselves. So please encourage children to ask by themselves. So instead of typing or letting you ask, I think they should turn on their camera, have the question ready for Pankaj.
And you can ask me questions in English, Nepali, Maithili, Hindi, anything. It doesn't have to be English.
Yeah, Nirdesh, could you ask your questions? It's on the chat though. Please turn on your cam and then please ask your question.
Yeah, I have a question. So if you know about 0G, which is a plane trip that you go on, and you experience zero gravity, but the plane is actually not in space, but you still experience the full zero gravity effects. How is this exactly possible? I would like to know, and I'm very curious.
So it's like you said, it's not natural gravity. In fact, there's no space with natural zero gravity at all. Even beyond far reaches of any heavenly body, there's some gravity that's there. Like I talked about the International Space Station, it's about 300 something kilometers away from Earth, but it still gets pulled down, and you have to boost up the orbit. How do you get a simulated gravity? It's through rotation sometimes. So when astronauts go to space, their whole bay, sleeping bay, and everything is rotated really fast to simulate gravity. There are artificial ways to do that, or you could use other forces that can counterbalance gravity, and it would feel like you're in zero gravity, but you're actually not in. So there's a lot of, there's a lot of engineering that goes into it. And I would say it would not be possible for me to, explain the whole thing completely in the time frame that we have. But yes, it's pretty much, the concept is to counterbalance the effect of gravity. Well, whatever forces you're getting from gravity, counterbalance it through rotation, centrifugal, centripetal force, and then you should have it. Sometimes they use really powerful magnets to lift up the capsules itself, but there are ways to do it.
Oh, okay. Thank you.
Pankaj, there's a question on Facebook. Are there anyone who is not from science background in NASA?
Oh yes, absolutely. You have people who are really good at communications, people who do a lot of legal stuff, people who do a lot of artwork. So a lot of artwork goes into designing these things. So yes, there are people from all around. Medical doctors, yeah, you name it. NASA hires everybody, but there's a bigger chance to get hired if your background is science or engineering, but it doesn't have to be.
So there are 3 raised hands. Ronak, do you have question? Nancy, you have to wait for your second question. Let others ask. Ronak, do you have question?
Yeah, I don't get why there wasn't Ton 618 in like the planet showcase. So the Ton 618 is a lot bigger than the sun. It's the biggest black hole ever. No, I don't get why it wasn't there.
Wait, I could not hear you. Could you please repeat your question again? I'm having trouble hearing you.
I didn't see Ton 618 in the planet showcase. I'm curious why. Because it's the biggest black hole.
I can hear you properly. Tons of what?
I didn't see Ton 618 inside like the showcase.
Mhm.
And Ton 618 is definitely smaller than a galaxy, but I didn't see it before galaxies.
Right. See, so that simulation, we cannot compare every single object that we come across, right? I mean, there are pulsars, there are exoplanets. There's a lot of things. What I was trying to demonstrate is just the scale of things. So how bigger is man-made objects compared to dwarf planets, and then actual planets, then exoplanets, then galaxies? But there's a lot of things. It's a whole spectrum. There's a lot of things that was not included in there. There's millions of objects that I cannot include in that presentation. But it's a sliding scale. There's a lot of things in that scale that was missing.
Okay.
The next is Adya Jha. You have to unmute yourself. And please press the reactions, raise your hand.
Yeah. I was reading that there's been a recent study that the presence of dark matter might not actually be confirmed. Like I was reading that there has been evidence that external forces can affect the data we receive. So is it possible that dark matter and dark energy aren't actually like the correct answers to this question about like why is so much of the mass in galaxies not visible?
See, the core of this question is the word dark. Like I said, anything that's unknown, we categorize them as dark. So the dark matter and dark energy, you cannot really see, just like you cannot see air, but you can see their effect. You can see how leaves move, and you can feel the wind and stuff. You can feel the effect, but you just don't see it, right? It's the same thing with dark matter and dark energy. We don't really understand what they are. For now, we just categorize them as dark matter. Some of these things we understand a little bit. We call them exotic matter. It's matter that's not ordinary, right? And it's in the transition between ordinary matter and then dark matter itself. But dark matter definitely exists. Do we have accurate data on that? Like you said, no. We don't know what's affecting what. Like I said, if there's way too many unknowns, if you're in the room and there's 15 people in that room throwing stuff at you, you would not know who threw what, right? You would feel the effect. You would know there's something coming up. You wouldn't know what the source of it is. So a lot of dark matter and dark energy is unknown, and we don't know what's causing what. And it's an active area of research.
I had a question.
Yeah, I see Mukesh, the screen name called Mukesh. He's been raising hand for some time. Mukesh, can you turn on your camera and ask the question? Or else let's move on to someone else.
Hi. Let's say you're really interested in being an astronaut, right? And you have to have like a background that you're really good at. What is one thing that you have to kind of be really good at to become an astronaut? Like a course, or like, let's say medical, right? There's medical and engineering. What is a specific one?
See, there's definitely more opportunities for people who have actual engineering and science background than other fields. Like you see, the three examples that I gave you, one of them was a medical doctor, right? So NASA needs people of all kinds, that they have all different kinds of experiments, and they send people of different talents. But just to become an expert in your field, focus on the skill set that's required for that skill. So for example, if I'm an engineer, I should be able to design stuff. Right, my skill set should not be drawing. It should not be, let us say, if I'm an engineer, my skill set is not helpful if I'm good at dance, right? I should be good at designing, right? I should be good at executing stuff. I should be good at building. So the skill set that's required for any field is the key. That's number one. And if you are in the United States, you have a lot of opportunities here to explore. But if you're outside the United States, for example, if you're in Nepal, unfortunately, we do not have a space agency, but there's a lot of there's a lot of new organizations that's coming up, and you can get involved. So getting involved and developing the skill sets for your particular field are two, I would say, two prerequisites to becoming an astronaut.
Thank you.
I'd like to add something to that. You know, a lot of astronauts come from the military background, so you also have to have you have to be really fit to be an astronaut. There's a lot of things, a lot of biological changes that go in once you're in space. So a lot of majority of astronauts actually come from military background. I was in the military once, and then the applications for astronauts opened, but that is not where my interest was. I wanted to be a theoretical physicist. I'm not saying that I would get selected. I'm just saying that I did not even apply. So you have to be very clear on what you want to do in life, because once you're into the astronaut corps, it's several years of training, and then only a few people actually get sent to space. A lot of them have to wait in the bench. So I would say focus on becoming an expert in your field, and then becoming an astronaut is secondary.
I see. Do we have time, Pankaj, to take
Yes.
last 3 questions?
Yes.
3
One
questions?
moment. Yes. We have time. That's
Okay.
cool.
So we have time. So I see Sandesh, Nancy, Cindy, and Mridula, your kids also have questions. So yeah, kindly take your turn. Whosoever is ready can go ahead with the question.
Yeah, so I had a question about going back to the matter and dark matter.
Mhm.
Is antimatter also considered dark matter, or if not, what is it exactly, antimatter? Because when I look it up online, it's not very clear. Like they don't really explain it very well. So
Okay, if you understand it, it's not dark matter. If you don't understand it, it's dark matter. Anything you do not understand is vaguely categorized as dark matter. For example, we understand what the antimatter of electron is. It's it has it's an entity it's a subparticle that's very similar to electron, but it has opposite charge. It's called positron. Electron is negative. Positron is positive. It has a lot of properties that are similar to. I would say it has a lot of mirror properties to an electron. And so far, if antimatter is dark matter, if you know it, if you understand it good enough, it's not dark matter. Anything that you do not understand is dark matter. If you anticipate that there's a subparticle and you think it could have antimatter, if it's not known yet, you can say if it's not known, it's dark matter. If you know it, you cannot call it dark matter anymore. That's the key.
So is there been enough research for antimatter to be considered actual matter, or is it still considered dark matter?
No, everything in space. We are just starting. We are not even at the tip of the iceberg. So a lot of things are still being discovered. A lot of things in astronomy that you see now, especially interstellar space, where You have a lot of free particles. It started at the beginning of the 20th century. So it's a very active area of research. And antimatter, if it exists or doesn't, it definitely exists. How much of it is known, how much we do not know, we don't even know that. We don't even know how much we do not know in space. Let's start there.
Got it. Thank you.
Thanks.
Next question, please. Nancy.
So, like Kepler 2020b is like similar to Earth. So, my question is, have you sent like robots, or like has there been a person on Kepler 2020b?
Unfortunately, no. The only place we have been able to send people was on the moon. So, for example, if you want to go a little further than the moon, the planet Mars comes first. It will take about 6 to 9 months just to get there. And a human being can get frustrated in 6 to 9 months. And you need a lot of supplies, a lot of food, and there's psychological elements that go into effect. So just our solar system, we haven't not even been able to explore our solar system. Exoplanets, there are billions of miles away. That's not on the menu for, I would say, at least 100 years. It's not even on the menu. In the next 20, 30 years, we might be able to explore our own planets, probably Mars, or Jupiter, or Saturn. But exoplanets like the Kepler, the very Earth-like planet Kepler that you mentioned, it's way, way too far away.
Cindy, you are next.
My question is that I'm in high school right now. What classes should I take to really like understand astronomy and aerospace? Because I don't really know anything about it right now.
Okay, so at this stage, I would say study things from outside your course as well, because your curriculum itself will not cover a lot of stuff, right? Your curriculum is standard, it's designed for everybody, but since you are interested more, you can explore on your own, read books that's outside your course, but specific things that you could do now, focus on calculus. Are you taking anything in calculus now, or higher level math, anything higher level?
Yeah, I'm gonna take honors algebra 2 next year, and then pre-calculus after that.
Okay, that's wonderful actually. So focus on calculus, mathematics wise, focus on calculus. Science wise, step out of your curriculum, read things from outside, and try to learn some programming. These things, 3 things. And something non-scientific, focus on your communication skills. Without good communication skills, you cannot succeed in any other field. Like I have a lot of brilliant ideas, but my speech is not very fluent, right? And it causes me trouble sometimes. So try to focus on your communication skills, I would say.
Okay, thank you so much.
Thank you.
I do see Arsh Mahto and Aradhya Mishra, you'll be next. So Arsh, please go ahead.
So I just had a question on like space travel for humans pretty much. So do you think like a company like SpaceX, right, is promoting like travel to like different planets pretty much, and they think about like publicizing it? So do you think that's like actually a good idea in your opinion, or should it just be like not really possible?
No, it's totally possible, and it's a very good idea. Like I said, the planet Earth is the cradle of human race. So like just a baby has to at some point climb out of that cradle and explore. Us as a species will climb out of Earth. We will explore more planets, and this is a good starting point. And I'm sad that a lot of government agencies are not focusing on this. I'm glad we have somebody like Elon Musk and SpaceX who's aiming that high. I mean, in our lifetime, you'll see people colonize other planets. How old are you now? If you don't mind me asking.
I'm 16.
Okay, in your lifetime, you'll see people land on Mars, and then you will see probably a temporary colony. I don't know about a permanent colony, but people will colonize other planets in our lifetime, and that's a good thing. Let's say what if something happens to Earth? If it gets hit by a big comet or anything, and it becomes unlivable, right? If you have colonies on other planets, you could survive. The human race could survive, so it's a good thing.
Thank you.
Next is Aradhya Mishra.
Yeah, I have a question that when astronauts are in space, is there a place like they can take off their helmets? Because in space they stay for a very long time, do they have some place that there's air and they can take off their helmets and everything?
Yes. So when you are inside the space station or inside the space capsule itself, there's an artificial environment that's made for you. Earth, like, I mean, you cannot have much gravity, but other than that, there's oxygen and there's everything, and you pretty much live like a normal. Let me show you a picture. Give me 1 second. Okay, so this is people living in space. This is inside the International Space Station. Can you guys see my screen? See all these people? That's how you live in space. When you are inside the capsule. But if you go outside these capsules, when you don't have Earth-like environment, you don't have oxygen, there's too much radiation, you're pretty much hanging out, then you have to gear up. Let me show you some. Okay, this is when you're outside your probe. So these people are outside the space station and they're doing some work. They have to gear up. Inside, you can just dress up casual. That's a good. That was a good question. No, all these questions were good. I'm sorry. This was a great question for a small kid, but all these questions that you guys are bringing up are really great. I'm happy.
See one question posted on Facebook by Monica Kurd. What is the difference between rocket and Starship?
Okay, so there's no such thing called a Starship. There are eventually rockets, and the rockets take space capsules into space. This company called SpaceX, it's calling its rocket. It has named its rocket Starship, right? So it's like a brand. Like you can have a lot of detergents, right? You could have Surf, you could have Tide. There's a lot of detergents that you could have, and then companies can brand it. So SpaceX has branded its rocket as Starship. That's the name for the big rockets that are supposed to take people to space. But yes, essentially they're all rockets.
So I do see those who have asked the question, you can erase that raised hand sign that confuses me. If you have done so, Nancy has third question. But before Nancy, does anyone else have question? And Nancy can definitely go ahead if no one has a question.
Yes, Subha has a question.
Okay.
Yeah.
When will people be able to go on Mars? Live in Mars?
I would say a few decades from now. It might be 10 years at least. Elon Musk wants to rush. He wants to send people to Mars as soon as possible. But I would say it would take a decade at least. It's a little far. I would say it's not that far. It's about a decade.
Okay, thank you.
Nancy, yeah, unmute yourself.
So, like when comets or rockets enter our solar system, they disappear because like our mass, they turn it into small bits and like it doesn't hit like that much. But why when rockets like go up, why doesn't it disintegrate?
It is supposed to disintegrate. It's designed that way. So if you're building a huge rocket, you need a lot of fuel, right? So you add a lot of boosters and everything, but you don't want to carry all that weight all the way up there. So once that fuel is used from the boosters, it is designed to fall down. Some of these companies, they are trying to reuse these parts that fall down. So for example, SpaceX has reusable rockets. Some of these companies, they just let their parts fall down and disintegrate on their own. But everything is planned. It doesn't just happen randomly. You know where these objects will fall, so it doesn't fall in a community, a city, or a town. The trajectories are planned.
Pankaj, we have a great participant online. He is Dr. Rakesh Mandal. He is oncologist, and even I see him raising his hand. So Rakesh ji, apne question पूछल जाओ. राकेश जी अहाँ म्यूट पर छी.
like, what is gravity? Like, not just like the basic, but what is gravity? Like, does gravity actually exist?
So this is not something we could answer in a few minutes. It's huge. So there are four fundamental forces in nature. We have the strong and weak electromagnetic force. We have nuclear forces, and then there's gravity. Gravity is actually the weakest force that we know. It might sound weird, but it's by observation. Gravity is one of the weakest forces of fundamental forces of nature. Well, it comes from the curvature of space and time, but if I try to answer this question in a few minutes, I will give you an incomplete, confusing answer. But for now, just try to understand it comes from mass and the curvature of space and time. It's one of the fundamental forces of nature.
All right, thank you.
Next question is Abhiraj. Abhiraj from Pittsburgh. You can ask the question.
So my question was, are we ever in future able to travel at the speed of light?
See, that's a trick question. A lot of the intuition is we cannot attain the speed of light as as living entities. Artificial objects probably yes. But if your question is about traveling towards light, let me give you an example. Have you seen a lot of these okay, forget about that. Okay, you know how a fax works, right? A fax, you have a piece of paper, it has some information, and then you input it here, and so somewhere in a different part of the world you get the same printout. What happens is whatever information you have is converted into electrical signal. That electrical signal passes somewhere, and then it's decoded into that information again. It's the same thing with us. If we're ever able to attain the speed of light, it would not be us traveling. It would be more like converting yourself into a signal, and then the signal goes somewhere, and then it appears, reappears. It's pretty much a transformational process. So, who has seen Mahabharata or Ramayana? Anyone? Nobody has seen Mahabharata, Ramayana, anything?
I have.
I just finished Mahabharata yesterday.
Okay, so you see how gods disappear. There's a flash of light, they disappear, and the flash appears somewhere else, and they appear again. It's the same. So the matter gets converted into light. That light travels somewhere, and that it's converted back to matter again. So that's one way it's possible. But so far, traveling at the speed of light in the form and shape we are in, that's a little far-fetched.
So not anytime soon.
Speed of light, I would say not anytime soon. Yes, that's a good way to put it.
Thank you.
Thank you.
So next is Atiksh. You can ask the question.
Okay, so my question is, when people are able to habitat Mars and come to Mars, I heard that once they come to Mars, they can't get off of Mars. Is this true?
See, that would be a case in the beginning. So when people first came to America, it was a one-way journey. So people came from Europe and other parts, and they just settled here. There wasn't, a way to go back and forth. And especially if you are trying to colonize a place, you have to pretty much create a settlement. And it's really expensive, and it takes a lot of time. Like one-way journey to Mars is anywhere between 7 to 9 months. So that's why logistics, it's not scientifically impossible, but logistically it's a challenge to just ferry people to and from different planets in the beginning. But gradually, when we have better technology, yes, I mean scientifically it's totally possible. It's more of a logistical question.
I did see Sanjay ji's daughter from Chicago. I don't know her name. Unmute yourself and ask the question.
My name is Angel Singh, and my question is, when was the solar system made?
See, there's a couple of different theories. One of the theories is that there was a lot of dust and gas, and the sun formed, and other entities got captured, and the solar system gradually formed. But its exact case, it's conflicting. I would not give you that answer. It depends on the theory you're looking at. So I'll give you an example of how any star planetary system is formed. Initially, it's just a lot of gas and dust. But if there are higher elements in that gas and dust, anything that's higher than hydrogen and helium and other things, there is a chance that it will condense gradually, and that condensed entity, if it's big enough, it can become a star, and then it can host its own planet. So giving an exact age of the solar system would be inaccurate, because it depends on a lot of hypotheses that you have, and I would honestly not answer that question. I mean, you will find people who will tell you right away, okay, the universe is 13.77 billion years old, but no, I would pause on that question and see. It depends on what theory, what hypothesis you're looking at. The process is more important, I would say. The process of formation is more important. And if you don't know how it was formed, we don't know how long before it was formed.
So, we should conclude today's event, and if you give me permission, then yeah.
नहीं दीदी एक सेकंड अपने दीदी पंकज जी हम बैकग्राउंड अपने काइन मतलब बैकग्राउंड नहीं सुन लो कि हम मिस कर ले, लेकिन किड्स सब के हमने के एक बेनिफिशियल बताए कि अपने एक बैकग्राउंड बता दियो, एजुकेशनल बैकग्राउंड, ताकि ओकनियो के इनकरेज बताई, दे आर गोना follow you.
Okay, great. So this question I will try to answer immediately so that we are more inclusive, right? हमर जन्म तकरा बाद ग्रोइंग अप नेपाल में भेल, जनकपुर में। हाई स्कूल में रहिए तो हम सब बहुत ज़्यादा इन्वॉल्व रहिए साइंस में, मतलब ये हमरा सबके की बन गेलै जे कि हम सब किस विद्यार्थी सब जे सब इंटरेस्टेड रहिए साइंस में, हम सब पहिने हाई स्कूल में आ तकरा बाद हाई स्कूल सबके बीच में आ तखन सिटी लेवल पर जे छै से साइंस क्लब सब बनेलिए आ साइंस में इन्वॉल्व रहलिए हाई स्कूल तक। मतलब डिफरेंस एतबे रही जे कि अहाँके केकरो मतलब म्यूजिक निक लगे छै, किनको स्पोर्ट्स निक लगे छै, तो सब ओहि में इन्वॉल्व रहे छथिन, हम सब साइंस में इन्वॉल्व रहिए। नहीं तो बाकी सब नॉर्मल जेना आरो विद्यार्थी सब रहे छथिन नेपाल में, तहिना हम सब रहिए। तकरा बाद +2 के बाद हम एलिए यूनाइटेड स्टेट्स, ओक्लाहोमा, यूनिवर्सिटी ऑफ सेंट्रल ओक्लाहोमा, ओहिठाम हम बैचलर खत्म के लिए इंजीनियरिंग फिजिक्स में, ओहूठाम हम इन्वॉल्व रहिए, मतलब रिसर्च सब में, अपनो किस चीज सब डिजाइन के लिए, किस प्रोजेक्ट सब में असिस्ट के लिए प्रोफेसर सबके। तकरा बाद जे छै से मास्टर्स हम के लिए यूनिवर्सिटी ऑफ वाशिंगटन साइठम। तकरा बाद एहि साल हम जे छै से PhD करऽ जा रहल छी। तो मतलब हमर बाय एंड लार्ज जे हमर करियर इवॉल्व भेल छै, जे हमर करियर साइंस के सेक्टर में अखन तक पहुंचल छै, एमे छै एकटा बड़का फैक्टर छै इन्वॉल्वमेंट। मतलब यदि अहाँ के कोनो चीज पर पैशनेट छी तो अहाँ ओहि पर ज्यादा से ज्यादा टाइम स्पेंड करियो। अहाँ कथी पर टाइम स्पेंड करबै दिन में, उहे अहाँ के मतलब यू बिकम व्हाट यू डू ऑल डे। अहाँ अपन 10 दिन के लॉग राखू, अपन देखियो अहाँ दिन में ज्यादा से ज्यादा टाइम कथी में स्पेंड कर रहल छी, बहुत ज्यादा चांस छै जे कि अहाँ उहे बनि जाब लॉन्ग टर्म में। यदि अहाँ गिटार बजेबै छी लॉन्ग टर्म, तो अहाँ के मतलब देयर इज अ गुड चांस यू बिकम अ गिटारिस्ट। अहाँ के साइंस में इंटरेस्ट है, साइंस पढ़ू। हम ई नहीं कहै छी सबके साइंसे पढ़ू, लेकिन मतलब अहाँ के जे फील्ड में इंटरेस्ट है तै पर मतलब लागल रहू, से छै इम्पोर्टेंट। एक आरो बात, पेरेंट्स यदि अहाँ सब सुनि रहल छी तऽ एकटा आरो बात हम कहऽ चाहब। कंपैरिजन जे अपना सब में एकटा छै जे कि बच्चा सबके बहुत जल्दी अपना सब कंपेयर करै छियै। कंपैरिजन किछ हद तक कॉम्पिटिटिव कंपैरिजन जे छै से ठीक छै, बढ़िया छै। मतलब कंपेयर करू बच्चा सबके, वो मैथ में बढ़िया छै तो हमर बच्चा केना मैथ में हैत, किछ हद तक छै। लेकिन बहुत ज्यादा कंपैरिजन जे छै से बढ़िया बात नहीं छै। अहाँ सुनबै जे कि अहाँ सब सुनबै जे कि कंपैरिजन से बच्चा सब ह्यूमिलिएट होइ छै, चाहे बच्चा सब डिस्करेज होइ छै, वो फैक्टर सब अलग छै। एट द कोर कंपैरिजन जे छै से एकटा डिस्ट्रैक्शन छै। अहाँ के बच्चा सब में एकटा हरेक बच्चा में किछ ने किछ इनेट टैलेंट रही छै। रूम में जते आदमी छी अपने सब आदमी किछ ने किछ एहन कह सकै छी जे बाकी आदमी नहीं कह सकै छी। सुनऽ में वियर्ड लागल, लेकिन हरेक आदमी में किछ ने किछ स्पेशल रही छै। जखन अहाँ बच्चा के कंपेयर क दोसर बच्चा से मतलब ज्यादा हेल्दी अमाउंट से ज्यादा कंपेयर करै छियै, तो बच्चा अपन टैलेंट से ज्यादा वो अलग दोसर बच्चा के टैलेंट पर फोकस करऽ लगै छै। तो ओकर अपन टैलेंट से, अपन इनेट नेचर से जे छै से डेविएट होइत जाइ छै। ओकर जे अपन इनेट टैलेंट रहै छै वो एक्सप्लोर नहीं करऽ पबै छै बच्चा। तो बहुत ज्यादा कंपैरिजन ठीक नहीं छै। बच्चा के टैलेंट कथी छै तै पर मतलब तकरा आइडेंटिफाई करऽ के कोशिश करियो। वो एके बेर में नहीं हेतै। शायद अहाँ के बच्चा कहियो प्रोग्रामिंग, कहियो मैथ, कहियो किछो पकड़त, कहियो एक्सप्लोर करते, लेकिन इवेंचुअली वो अपन रास्ता पकड़ते। तो बच्चा के जैसे एक्सप्लोर कर दियो, मैच्योर हो दियो, मतलब से ज्यादा इम्पोर्टेंट है।
जी जी बिल्कुल धन्यवाद पंकज जी टाइम लिमिटेशन से अपना हो के हमने के बेसी टाइम नहीं ले सकम लेकिन ऑफ कोर्स थैंक यू वेरी मच फॉर योर वैल्यूएबल टाइम आज के प्रोग्राम बहुत निक भेल वी एक्सपेक्ट कि बच्चा सब बहुते सीखने भेट आज के प्रोग्राम से I would like to request kids, if you have any question, just email us. Pankaj is going to provide his email address to us, and then we are forwarding your question directly to him. He's going to answer if you have any questions. And then thank you all participants for today's program. It's really amazing. We got a lot of information, Pankaj ji. Thank you. Prajita Didi, please, side notes, apne ke final notes
Pankaj ji, it was an enlightening experience for parents, kids, to delve into the world of space and astronomy and career and pathways to think of as early as elementary school children and onwards. Definitely, there were a lot of things you have talked about, and especially the high schoolers who are, very close to applying to colleges. And you did talk about how these things branch out. And you did talk about the job prospects, comparing aerospace to astronomy. And those things do not come that easy to parents, how to encourage and motivate and give them some factual information. So thank you so much, Pankaj. And the kids, get inspired. That was the motive behind this webinar, Zoom program. Get inspired. As he said, that, if you have made up your mind that you want to do certain thing, you just remain passionate, stick to it, and you will attain a level in that field. Like Pankaj did himself. In Nepal, he dreamt of pursuing a career in science, and he joined science clubs. He came to America, and then he kept on working towards that dream. And he had reached this far, and he's starting a PhD in space science. So that's amazing. So we have to be inspired. And if we compare you with our neighbors' children, that also I learned. I do a lot to my kids. I should not do that. And every child has innate quality. They have that needs to be nurtured. And if the parents are hearing, we have I have to say the same thing, echo Pankaj's word, that encourage that talent. So Pankaji, you have no idea what you have done to our children today. It's a miraculous, it's a phenomenal. We did stargazing through your presentation. In a cloudy and snowing northeast, we have seen everything through your lenses. So thank you so much. Anta is forever indebted to this presentation. And kids, say thank you to Pankaj. And and we look forward to hear from him in future what he did in space sciences. And we would invite him again to come to another Zoom program. And with that note, with heartfelt gratitude from Anta family to you, Pankaj. Thank you so much for coming and explaining everything. It was quite comprehensive presentation in my mind. Thank you.
Thank you, Prajita ji, and thank you, Anta. Thank you for being so proactive. It's great. And the questions were great. Some of these questions I was not able to answer completely in the time frame that I had, but they were really great questions. I would encourage you to keep exploring. And if you have any questions, you can send me by email. I might not be able to reply right away, but I will get there. And some of these tools that I introduced to you, I'm sorry I was not able to make it like a comprehensive class, but explore on your own. If you have any questions, I'm there. And thank you so much, everyone. Thank you, Prajita ji, and thank you, Anta.
पंकज जी अपने विंडोज क्लोज कर देवल जाए तो हमने के डिस्कनेक्ट.
Okay, so I'm ending the meeting here now.
Have a wonderful day, Pankaj ji and kids.
Thank you, everyone.
Thank you.